Thank you very much. First of all, thanks to the organizer for this invitation. I'm really glad to talk today. I'm going to talk about joint work with Carlangelo Riverani. And before, let me start with some motivation and aims. When we usually in smooth ergodic theory, you are interested into a smooth map from a smooth compact Riemann manifold, which satisfy such condition in condition 1. And this avoid actually singularities situation or behavior nearby critical points or infinite measure systems. They are all interesting in applications, but for this talk, I'm going to talk about this kind of map. You can think about F as a diffeomorphism or a local diffeomorphism. If the system has no natural invariant measure, such as in the conservative case, for example, in the Hamiltonian case, you have the Liouville measure. You may wonder if there are any measures which are invariant under the dynamics, and they are more compatible with volume when the latter one is not preserved. For example, in the case of dissipative systems. These kind of measures were rigorously defined by Sinai-Ruelle-Bowen in the 70s. In this talk, I'm going to use the same terminology for the SRB measure and the physical measures. The physical measures are F invariant probability measure, for which the basing of attractors here is a set of positive Lebesgue measure. But of course, in general situation, they do not coincide for sure. So if you're curious, you can take a look at this enlightening discussion by Lasse Young about the differences of these two objects. In our case, they do coincide, so I will use this definition. So it's the set of points for which the empirical measures converge weakly to the measure. So the existence of such a measure is not a trivial question to answer. Then maybe you can ask about the uniqueness. And once you know that, maybe you can initiate to study more statistical properties such as mixing, decay of correlations, central limit theorem, and so on. One well-known class of systems that they are well-known studied from the statistical point of view are the uniformly hyperbolic system, in which you have a splitting of the tangent space into contractive and expanding directions. So in one direction, you are expanding the vectors, and the other one, the stable direction, you are contracting it. A little less is known if you go beyond the uniform hyperbolicity, for example, in the case of non-uniform hyperbolicity, or just the case on which we focus, which is the partial hyperbolic case. And you allow the system to have central directions, which are dominated by hyperbolic directions. So let us move on the assumptions and the kind of systems that we have studied. Here, F is a local diffeomorphism from the two torus to itself, so we are in 2 dimensions. And the very first assumption is quite natural in this situation, which is the existence of 2 families of invariant cones. The first one is the unstable cone, which is invariant forward under the dynamics. And the other one is the central cone, which is invariant backwards. And the characterization of these 2 cones are that if you take a vector inside the unstable cone, you are expanding the vectors by a factor lambda, which is greater than 1. And in this case, it strongly dominates what happened in the other directions, the other direction, which is the central one. In which you may expand or contract the vectors by a factors mu plus or mu minus, respectively. And we are mostly interested into the case on which mu plus is really close to 1, as one can imagine. The third assumption is about the preservation of a family of curves. You take closed curves, smooth, such that they do not have zero tangent vectors everywhere, and they have a homotopy class 0, 1, so they wrap once around the torus, and in each point, the tangent vectors to these curves belong to the center cone. So the assumption is that you want this family of curves to be preserved by the dynamics backwards. This is a bit technical, more technical assumption, and it is related to the Banach spaces that I will introduce later on. The first assumption is a pinching assumption. And as you can see, the domination here of the expansion over what happened in the other direction is strong. This number here, zeta r, which depends on the regularity of the map, can be definitely improved, but in our case is irrelevant since, as I said, the mu plus is taken to be very close to 1. So we can define F as the strongly dominated vertical partially hyperbolic system. For this talk, I will use SV for sure, if it satisfies these 4 assumptions. And the first example that we had in mind for an SV system is this family of maps parameterized by epsilon running from 0 to 1, in which the first coordinate is an expanding map only along the horizontal direction. And in the second coordinate, we have a perturbation of the identity if epsilon is small enough. And you can see that if you take epsilon equal to 0 here, since small f is an expanding map on the circle for each theta, you have infinitely many SRB measures, because each one of these map has an SRB measure, and you have strong statistical properties. So you have exponential decay of correlations. So you can see that if epsilon is equal to 0, the system has infinitely many invariant measures. So as long as you perturb the system, you may expect some interesting behavior. If epsilon is equal to 1, you have a quite general system. So you want to check for whether the system is an SV system or not. This is what we have here, and under these conditions, you can prove that the system is an SV system. Without going into the details, the main characterization of these conditions are that the partial derivatives of f, small f and omega, they must not be too big. An immediate consequence of this result is that if you take epsilon small enough, then f epsilon is actually an SV system. So if we take a look to the literature, we can see among all the results about partial hyperbolic systems, there are plenty of them. Maybe one of the closest one to this situation is this work of Tsuji, who proved that generically an endomorphism, a partially hyperbolic endomorphism in the two torus emits finitely many physical measures. The problem here that this genericity is not quite, is not trivial how to check this genericity for a given system, such as the fast-slow system F epsilon. On this, concerning F epsilon, we have these 4 papers, mostly written by De Simoi and Liverani, which contains more detailed results about from the quantitative point of view, and also many results about the limit theorems associated to these systems. For example, here they prove the existence of a physical measure only in the mostly contracting case. So they assume that the central exponent, the central Lyapunov exponent of the system is almost everywhere negative. In particular, the technology that they use it's a bit involved, and we may wonder if there is some more efficient way to obtain similar results in order to generalize this result to models which are more realistic, let's say. So one one possibility is to use the very famous functional approach. The main character here is the transfer operator given by this formula. The main characterization of this the transfer operator is that the fixed point of it corresponds to the density of the absolutely continuous invariant measures. So what you want to do is to look at the eigenvectors associated to the eigenvalues of modulus 1 of this operator. And the question becomes if there exists a Banach space included in L1 in which the transfer operator has a spectrum which is the full disk, which is very little information. So you may want to find a Banach space on which this operator acts as a quasi-compact operator. As the terminology suggests, the picture here is the ideal picture for the spectrum, in which apart from a smaller disk which goes to 0, you have infinitely many eigenvalues. So from the abstract point of view, you have this theorem, which is quite general in functional analysis in this, and this is what we need. The ingredients are two Banach space, one stronger included in the other one, and two inequalities called the de la Sota-York inequalities, and plus compacted results of the strongest space into the weaker one. So under these conditions, L is a quasi-compact operator, and you have an estimation of the essential spectral radius and the spectral radius. So this is what we would like to obtain for our system. Still, looking at the literature, the first case, as far as I know, studied using this approach for how concern something close to a partially hyperbolic system is this model here. Actually, here I'm cheating because this is a uniformly hyperbolic, since on the second coordinate you have a contracting factor. On the first, this is a skew product over an expanding map. So the first coordinate is a linear map and is expanding. And it was studied by Tsuji first, who proved the absolutely continuity of the measure. And then by Avila, Gusel, and Tsuji, they proved that actually the measure belongs to the Sobolev space W2S. And this is true for almost every fiber here. What we want to do is, using more or less this idea, this approach, obtain similar results when F is an SV system, and then apply these results to fast-slow systems if it is possible, of course. So the first thing is to understand what this genericity really means in such a practice example. Actually, in the general case, Tsuji, you learn from the paper of Tsuji that this transversality condition, this genericity condition, is related to the transversality condition of unstable cones. I would prefer to use a picture here without, and avoiding any details. But the situation here is pretty simple. You take two pre-images of the same point, and then you follow the evolution of the unstable cone under the dynamics, and you compare these two cones. What you want to count is the number of pre-images that at time n have non-transversal cones. Of course, you may imagine that the smaller this number is, the better. And indeed, Tsuji proved that generically this number is small. And in this case, generically is about the surface partially hyperbolic systems in the two torus. In a very specific case, here we have a genuine example of a partially hyperbolic system. Butterly and Aslami proved that there is this correlation between n tilde, this number which counts the number of non-transversal cones, reaches its maximum values. So in this case, and in this Q product case, the maximum values is 1. If and only if the fiber is homologous to a piecewise constant function, And this is equivalent to prove the existence of an F invariant unstable direction. This is what we would like to keep in mind when we study our system F epsilon, which is not very far away from this system. So here is a first result about the SD systems, and we have proved that given F to be an SD system, sorry, here is a misprint, not vertical. If you can check that there exists N0 such that this condition is fulfilled, so you can see that the maximum value between these two numbers must be smaller than 1. This number depends only on S, which is the regularity of the sublet spaces. And this gives you a bound on the essential spectral radius. What you want to do actually is to check that this guy here is small, because as I said, the mu plus here in our case is very close to 1, and lambda is bigger than 1. So if you have a given system, this is a checkable condition, maybe using some computer assisted technology. If you prove that this number is small enough, you can check this condition, and so you can see that your operator associated to the map is quasi-compact. You find this Banach space. In the case of F epsilon, so we only need to check this condition, condition 4, which is the one that I just described. And as I said from the paper of Oliver and Teyman, we can use this idea, and actually we have proved that if omega is not cohomologous to a constant function, here the definition is a bit different, but is basically the same. This means that omega is cohomologous to a constant function with respect to f for each theta. If this is not the case, then you can find epsilon 0 and n0, and n0 does not depend on epsilon, such that the condition of the theorem holds for this epsilon small enough. So this is the results for f epsilon, and I would like to say a bit more about these results. This is the main technical results, which implies the theorem for f epsilon. Here I've written down the Lasota-Yorkes inequalities in this case, and as you can see, this inequality, this one is trivial since the operator is a contraction in L1, and this one blows up as epsilon goes to 0. This is not surprisingly, because for epsilon equal to 0, we already noticed that the system is not mixing, it has infinitely many invariant measures. So you cannot expect that this inequality converges for epsilon tends to 0. What we were interested in is to have more information on these exponents here, in order to have some more information on the bound of the eigenfunctions associated to the transfer operator. So paying the price to slightly enlarge the essential spectrum here, and losing a bit of the regularity, so taking S equal to 1, so we are in the sublet space H1, we have an explicit bound of the eigenfunctions of the operator. And for future works, it would be nice to improve these exponents here to have much more which can be used for using, for example, perturbation theory for f epsilon. In the remaining time, I would like to say something about the general strategy of the proof. This is a very, very rough idea. It's just to introduce the norms that we have used. So the first step is to get a geometric norm, to get a Lasota-Yorke for a class of geometric norms. So this is more or less the ITER that Avila, Suji, and Gusel proved for the simple case of a skew product. Here, the norms are a bit, they are related with to the norm that Liverani and Gusel introduced when they studied anisotropic Banach spaces in the case of hyperbolic systems. This is a slight modification on these norms. The main point here is to integrate along some admissible manifold. In this case, they are admissible curves because we are in one dimension here. And the point is to use this integration to get rid of the troubling direction, which is the central one. This class of curves, this class of admissible curves are related to the family of curves that I introduced at the beginning among the assumptions on the system. And if you have an Lasota-York inequality for this kind of norms and this kind of spaces, unfortunately, it is not enough because we miss the compactness of the strongest space into the weaker one. To solve this problem, you need to consider the Sobolev norms, the standard Sobolev norms in the two torus here. So the HS norm, and obtain a Lasota-York which mix together the geometric norms and these Sobolev norms. And here is where the transversality condition takes the main role. And we obtain this Lasota-York for a time big N, which in the case of f epsilon will depend on epsilon. And this is the case I'm going to show you in a moment. This is the reason why we have a Lasota-York that blows up as epsilon tends to 0. The third step is to mix together these two last inequalities to obtain the main Lasota-York inequalities in the right spaces, which are the ones with this norm here. And this is the last Lasota-York inequality. Sigma is a small number, is a number smaller than 1. And here we have the coefficients of the strong norm and the weak norm, which depends on the N0, which is the time of the transversality condition. And N, as I said, is this fixed number, which in the case of f epsilon depends on epsilon. So this is where the non-convergence of the Lasota-York inequality comes from in the case of f epsilon. To conclude, interesting questions could be to prove CLT theorem or a local central limit theorem for these systems. What if the base F is not just an expanding map on the horizontal direction, but is an Anosov map? So you have a contraction on the other direction. And at last, what if the fiber omega is higher dimensional? Because we strongly use the fact that the admissible manifold here to define the norms are curves. So we are in one dimension, and it's not completely trivial how to generalize these arguments if the fiber is higher dimensional, at least in the case of non-skew product system, such as the SV system that I described before. So I think that's all, and thank you very much for your attention.